Okay, good morning students. In this lecture we will discuss about the memory elements that we used in our CMOS circuitry. Okay, so this topic exist in your fifth unit. Also the same topic is in your third unit also. Okay, the third unit second topic array subsystem also contain the memory elements, that is SRAM, TRAM, DRAM, etc. Same topic also exist in your fifth unit memory element. Okay, so when we complete this memory element topic, so we complete the some portion of we complete the fifth unit, also the some portion of the third unit also. Okay, so let's start our topic. Memory element. What is memory element? Memory element is nothing but a sequential cells that are responsible to store some data. Okay, so any element that is responsible to store some data is known as memory elements. The memory elements is a very critical component that used in CMOS circuitry. Okay, CMOS circuitry is nothing but a combination of PMOS and NMOS. When we combine PMOS transistor and NMOS transistor for implementation of any circuit, then this type of implementation is known as CMOS implementation. And by using this combination, the circuit that is implemented is known as CMOS systems. Okay, so in CMOS system, this memory element is very important part. Okay, so before some decade, when we use memories, so there are various limitations of memory at that time, such as number of input output pins, number of driving input chip, number of input voltage, driving input voltage, its size, its speed, etc. These are the limitation of the memory before some decades. But after the implementation of this memory, in CMOS circuit, it is very we can implement various type of CMOS systems. By using this type of memories in CMOS circuit, we can implement various type of CMOS systems. Okay, so basically the memory elements can be divided into following three types. These are, first one is a random access memory, second one is serial access memory, and the third one is contained access memory. Okay, as name suggests that random access memory is nothing but a memory in which we can access the data randomly. It means that there is no limitation of the location of the accessing cell. Okay, we can access any type of memory cell and any type of memory cell from the location of the memory. Okay, but in serial access and contained access, there is some sequence through which we can access the memory cell. That's why this type of memory contains some latency time for accessing the data. But in random access memory, we can access any memory cell of any location. Okay, that's why the speed of random access memory is fastest compared to serial access memory or contained access memory. Okay, so this one is the basic structure of any memory. This one is the basic structure of any memory. We know that for implementation of any memory, we need a connection of bit line as well as word line. Okay, so we can also understand this as we need a combination of address line and bit line. Okay, so this decoder is used for providing the addresses. These row decoders are responsible for providing the addresses. It means that suppose I am taking a n bit address. So it means that by using this small n bit, we can generate locations. Okay, so and if each location and if each address consists a data of 8 bit, so we can say our whole memory size is 2 raised to power n cross k. Here k is the number of data bits. Okay, so any type of memory can be accessed, any type of memory can be represented by using this address line as well as the data lines. Okay, so and for accessing the data from this memory, we need some sense amplifier, buffer amplifier, write operator, etc. These are the operations that we need to implement in the circuitry for accessing the data. It is used in both time, at the time of reading as at the time of writing also. Okay, some theoretical portion of read only memory, RAM, all is mentioned here. uh, Random access memory is a volatile memory. Random access memory is a volatile memory. In this type of memory, we can read the data, also we can write the data. And for reading and writing the data, we need a very small time interval. But if I am discussing about the read only memory, in this type of memory, we can read the memory, also we can write the memory, but the writing time is very high in this type of memory. That's why this type of memory is only known as read only memory, because writing time is very higher as compared to random access memory. Okay, but in random access memory, read time and write time is very less as compared to read only memory. Okay, there are the two different types of we can divide random access memory in various different divisions. One of it is one of it is on the basis of its component. Okay, on the basis of component that we used in random access memory, we can divide random access memory into two types. One is known as SRAM and another one is known as DRAM. SRAM is known as static random access memory and DRAM is known as dynamic random access memory. In static random access memory, we use flip-flop and various sequential circuits for implementation of memory. But in dynamic read and random access memory, we only need a transistor along with a capacitor to store the data. Okay, so these are the basic type of random access memory. One is static and another one is the dynamic. We can also divide random access memory into further other types such as dynamic, static, load, synchronous, and asynchronous on the basis of clock pulses that we provide in the memory to access the data. When uh, when uh, when when we provide clock pulse simultaneously to itself to access the data, at that time this type of memory is known as synchronous memory, synchronous random access memory. But when we provide provide clock pulse serially, then at that time this type of memory, random access memory, is known as asynchronous random access memory. So these are the basic classifications of random access memory. These are the basic classification of random access memory. Okay, as name suggests, random access memory, in random access memory, we can access the data randomly. We can access the data that is stored in any type of cell. So we can say it is independent to the location of the cell. It is independent to the location of the cell. At any time we can access the data of any location. Okay, so here in today's class, we are discussing about some how can we read the data from the random access memory, how can we write the data from the random access memory. Okay, here this small square block is known as the RAM cell. This small block is known as the RAM cell. This RAM cell can be implemented by using several can be implemented by using several different elements. We can implement this random cell by using flip-flop only. We can implement this element by using the combination of transistor and capacitor also. Okay, and for accessing the data that is stored in this memory cell, we use this type of blocks such as sense amplifier, column mux, and the write buffer. Okay, the vertical line is responsible, line is responsible to provide the vertical line is responsible um, to provide the bit along with the clock. And these horizontal line is responsible to provide the word. These we can say this horizontal line is used this horizontal line is used to control the data. This horizontal line is used to control this memory cell, and this bit line is used to access the data. Okay, I'm explaining again. This horizontal word line is used to control this memory cell, and this bit line is used to access the data. That means we can write the data, we can read the data, or both operation can be done by using this bit line. Okay, and which time we want to access the data, this all time feature can be controlled by using this clock pulse. Okay, so this one is the simple diagram of generic RAM cell. Okay, any type of RAM cell. Suppose I'm considering the SRAM. Suppose I'm considering the SRAM. So in SRAM, we cannot use the capacitor. In SRAM, we cannot use the capacitor, but in DRAM, we only use the combination of transistor and capacitor for implementation of the memory. Okay, we can implement RAM by using the 5 transistor, by using the 4 transistor, by using the 2 transistor also, and we can also implement this RAM cell by using single transistor. Okay, in some transistor, in some type of transistor, suppose in some type of transistor, we can replace transistor by using some registers, because in this type of memory, the PMOS only used as a load. So we can replace it by using some register to reducing the power dissipation, for reducing the power dissipation. Okay, one SRAM cell circuit, one static RAM circuit is mentioned here. One static RAM circuit is mentioned here. Here, this word line is presented horizontally, and the bit line is presented vertically. Okay, the minus bit is nothing but a bit bar. The minus bit is nothing but a bit bar. So always the output that we find from this end and the output that we find from this side is complement with each other. That's why if I'm writing the bit in this end, so we need to write bit bar in this end. Okay, so by using this bit bar, by using the bit line, we can by using this bit line, we can take the output, from the memory. You know? Okay, and for accessing this memory, we use this word line. So by using this word line, we can access the data. Okay, so these two NMOS, one is connected here and one is connected here. These two MOSFET are known as accessing transistor. These two MOSFETs are known as accessing transistor. Okay, and we can say here two inverter combination is presented. One inverter is here because here one PMOS and NMOS is connected into series, and also here one PMOS and NMOS is connected into series, and the combination of these two inverter, one memory is framed. Okay, in this type of, so we can say if we connect the output of one inverter to the input of another inverter, and the output of the second inverter to the input of first inverter, so we can make a memory. Okay, so for making a SRAM cell, we need two inverters along with two NMOS. These NMOS are nothing but a access transistor, and these can be controlled by using bit line and word line. Okay, so for reducing the power dissipation, reducing the power dissipation, we can eliminate this PMOS. We can eliminate this PMOS by using only two loads. The range of this resistor is mentioned in the theoretical portion here. The range of this resistor can be vary from 100 Hz to 1000 megahertz. Okay, so this one, these are the structure. So these are the structure of simple static RAM cell. So these are the structure of simple static RAM cell. This one is the, this one is the layout. This one is the layout. This one is the layout. This one is the layout of, this one is the layout of your six transistor static RAM. How six transistor? One transistor, two transistor, three transistor, four transistor, fifth transistor, and this one is the sixth transistor. That's why this type of memory element, this type of static RAM is also known as 60 RAM. Okay, so for reducing the power dissipation, we can minimize the transistor. Okay, so we can implement the static RAM by using five transistor, transistor, three transistor, two transistor, one transistor, for reducing the power dissipation. Okay, so if you want to, if you implement the layout of the above mentioned static RAM, so that the layout will be mentioned here. So layout of 60 RAM is mentioned here. Okay, now here we see the how the read operation, how the read operation is performed in this type of cells, Okay, here you can see the capacitor is present over here. Okay, so when we connect a transistor with a capacitor, so this type of memory structure is known as DRAM. So this type of memory structure is DRAM. When we replace capacitor by using simple transistor, when we represent the capacitor in DRAM structure, we can also we can also eliminate the capacitor by using this type of, this type of transistor connection combination. Okay, here you can see only four transistors are connected to implement a memory cell. Here you can see one, two, three. Here you can see one, two, three. Three transistors are connected along with a capacitor to make a DRAM cell, dynamic random access memory. Okay, now how the read operation is performed, in this SRAM cell, how the read operation is performed in this random access memory. Suppose I am assuming that in read operation I am assuming that suppose one is in read operation I am assuming that suppose one is stored here, one means suppose VDD voltage is stored here. So if one is stored here, so because of this inverter, 0 bit is presented here. So because of this inverter, 0 bit is presented here, and I want to access this 0 bit, I want to read this 0 bit. Okay, so in which port we can read? We read this data from this data port. From this port we can read the data, from this port we can read the data, how this operation occur? At the starting, for this operation, at starting time we provide some precharge voltage to these PMOS transistors. Okay, we provide the VDD voltage, we provide the VDD voltage, we provide the VDD voltage, we provide the VDD voltage that is provided from here. We provide the VDD voltage to this transistor, we provide the VDD voltage to this transistor. At starting we provide the VDD voltage to this transistor. That's why the VDD potential is occur here, same as the VDD potential will occur here. VDD means you can understand it by using 1, and ground means 0. Ground means 0 and VDD means 1. It means that 1 is presented here. So to read the data, we provide a read signal, we provide a read control signal here. And from where we can provide this read control signal? We can provide read control signal from this word line. So when we provide the read bit, that means we provide 1, we provide 1 from the to the gate port of the transistor. This voltage is higher than the threshold voltage of this transistor, and because of that these transistors are in saturation region, and these are in operating condition. When this transistor and this condition are in operating condition, so it makes a short circuit path. it will make a short circuit path. These both transistors make a short circuit path, make a short circuit path. I already told you if one is stored here, it means that the potential in this side is VDD, so that the potential of this end and the potential of this end is equal. So we know that when the potential is equal, so no current is flowing through it, so that's why it won't works. But if we are discussing in this terminal, so here, because of this inverter, if VDD is present here, so here the ground portion, here the potential will be zero. So in this side of that, so in this type of transistor, one potential is VDD, and this type of transistor, one potential is zero. That's why we can say this transistor, this whole power, this VDD power will be dissipated from this side. Okay, this whole power, this VDD voltage will be dissipated from this side. That's why the voltage that we get in this end, so the voltage that we get in this end will be zero. So because of this power, because of this voltage dissipation. Okay, so now because of this inverter, this zero will be 1. So this zero will be 1. Okay, so by using this operation, we can see how we read the data that is stored here, how we read the data that is stored here. Because in of this topic, I told you one is stored here, that means VDD is stored here, and by using this operation we get the data that is stored here. Okay, so the same condition, if we are if we are providing, if we are considering the zero is stored here and one is stored here. Okay, if we are assuming that zero is stored here, zero is stored here. Now when we provide a red pulse, when we provide a red pulse, so that this will be short circuited, this will be short circuited. The no current is flowing from this side, no current is flowing from this side. Here some current is flowing from this side, because the potential difference is here, and because of the potential difference, whole power, whole voltage is dissipated here, and the bit will be zero. Okay, you can read the data from this terminal also. Also you can understand by you can read the data from this terminal also, because when the potential of this side and this side is equal, so no current is flowing from here, so no voltage dissipation occur. So that if voltage is VDD is presented here, so in this terminal the voltage is same VDD is presented here. VDD means here 1 is presented, and by using this inverter, we can 1 is converted into 0. Okay, so we can read the data in both in from the both port. We can read the data from this port, also we can read the data from this port. Okay, so I think you understand this topic, this read signal of this SRAM cell. The same circuit is presented here, the same circuit is presented here. Always remember that to read the data, first you need to provide the pre-charge signal. Always remember that to read the data, first you need to provide the pre-charge signal. Okay, so when we provide the pre-charge signal, so this transistor will works, this transistor will operates, and the this voltage, VDD voltage, will get in this end. Okay, so this is all about the reading operation. This is all about the reading operation of this SRAM cell. And the writing operation will same as the reading operation. The writing operation is same as the reading operation. What happened in the writing operation? What happened in the writing operation? In the writing operation, if the input is 1, in the writing operation, if the input is 1, if the input is 1 here, so by using this by using the SRAM execution, we can change the data that is provided here. We can change this 1 as 0. So if we change this 1 as 0, so it means that we can read that we can write the data. in this memory cell. We can write the data in this memory cell. So these are all about the reading operation and writing operation of SRAM. Here, here one sense amplifier is presented. Here one sense amplifier is presented here. Sense amplifier is nothing but an amplifier that is responsible for the comparison of bit and bit bar. That is responsible for bit and bit bar. When there is a difference, between bit and bit bar, at that time this sense amplifier compare this difference, and after amplification it will provides the output. Okay, so this one is nothing but this combination, this sense amplifier is nothing but a circuitry that is used for taking the output from this memory cell. Okay, so this one is all about the static RAM. So this one is all about the static RAM reading and writing operation. So I hope you understand this topic. In next class we will discuss about some row decoder and sense amplifier topic.